Okay, deformation. So there's a lot of words. Okay, but don't worry about it. When I show you how to solve it, right? You will say, hey, it's not that bad, right? So for this case, what is saying that we're going to have delta L, right, plus by delta R must be equal to 0. So we're going to impose this solution or this equation for statically indeterminate structure. And there's logic behind it. Not there's no logic behind it. There's reason behind it, which I'll show you later. So delta L is the deflection due to the real load. Or actual load, right? And delta R is deflection due to the redundant load.
Sir, sorry to interrupt. What do you mean by redundant?
Wait, I'm going to show you that. Okay, hold on. Okay, so this is just the theory part. Then later on, you'll see what do I mean by the redundant load. Okay. So from here, right, always take note. Important thing to take note. Okay, note is that delta L and delta R are always opposite in direction. Okay, so what do I mean? If you have delta L, you have delta R. If your delta L is positive, delta R must be negative. If delta L is negative, delta R must be what? Positive. Okay, they both cannot be positive, they both cannot be negative, because this entire equation has to be equal to what? Has to be equal to 0. Okay, it has to be equal to 0. So now I've uploaded some figures which I hope you guys did download. Okay, so this is one of the figure. Okay, so I'm going to copy. It's on Avenue to Learn. You should get them. Okay. Okay. So this is our learning example. So if you look at this structure over here, right, it's basically statically indeterminate. Okay, we cannot solve it by using summation about forces in the x direction, summation about forces in the y direction, summation about forces in the what, in the z direction. We can't do that. Okay, so I'm going to show you the solution procedure. So from here, I think I've convinced you. I hope I've convinced you. Convince you into the sense that this structure is statically indeterminate. Okay, so this structure is the structure is statically indeterminate. Okay, so from here, what we are going to do is we're going to do this. Okay, we're going to do this. So we're going to remove, right? So we know that this structure is statically indeterminate. We're going to remove. Okay, the first thing we're going to do is we're going to remove the support at point B. Okay, we're going to remove the support at point B. So when we remove the support at point B, right? So this is our pin section. This is our point A. Okay, so when we remove the structure, what will happen? It's allowed to what? Stretch. Yes or no? It's allowed to stretch. So now our structure is allowed to stretch now. So I'm going to draw it being stretched. Okay, so this is just a sketch. Okay, so half of it is stretched this way, and then the other half, right, is allowed to what? Move. Right, so we remove the structure, right? Hold on. We remove the structure, the support at point where? At point B, right? We remove the structure, the support at point B. Okay, so this is your point A. This is your point C, right? And this is now our point what? Our point B. And you can see our point B, it did shift, yes or no? You can see our point B, it did shift. And the shift is because of the loading at point D, right? So at point D, we have a load of 300 kilonewton. And at point K, right? So at point K, somewhere around here at point K, we have a load of 600 kilonewton. Right? So I'm going to draw a line across. So this is our original. Okay, this is our original. Right? So now, because we remove, what did we just do? We remove the support at point where? We remove the support at point B. Okay, so we remove the support away. Right? So when we remove the support away, right? What we have now, right, is we have this direction of deflection, and this is known as delta L. Okay, and we defined delta L earlier. So delta L is the deflection due to the loads or the actual load. Okay, right. Then the next one come in, right? So in real life, there is no delta L. Right? In real life, this beam is sandwiched in between the support of A and B. So what we did in the analysis is we took out support B, so it grown longer. Okay. Then after that, the next step is we're going to add the redundant load. Okay. At point D. Okay. So with the next thing that we're going to do, we're going to add the redundant load at point B. Okay, we're going to put it back. Okay, so again, I'm going to sketch our structure. Okay, now in this stage, when you put back the when you push it back to or when you induce a redundant load, you will not consider the applied load, the actual load. I repeat again, you will not consider the applied load, okay, or the actual load. So down here, when you see the way I sketch it, okay, this is our structure again. You see the way I sketch it. So again, this is our point A. Then we have our point D. Then we have our point C. Over here is our point K. Okay, so this is our point K. And then we finally come with our point B, right? So what the redundant load does is it's going to do this. Okay, so RB is the redundant load. Okay, so we push back redundant load. Okay, and what you realize is there's only the redundant load. We no need of at this stage. Okay, we don't need to consider the what? We don't need to consider the 300, and we don't need to consider the 600. Okay, so for at this stage, no need. Okay, at this stage, as in when you add the redundant load, no need to consider the actual load. For this case of 300 kilonewton and what? 600 kilonewton. So what we're trying to determine down here, right? We are trying to determine down here is we are trying to determine this now. Right? So we knew we had a deformation going down this way. Right? So now we're going to push it back. And this is your delta R. Okay, so delta R is the deflection due to the redundant load. Okay, so we're just going to push it what? Push it back. Okay. Okay, so this is how we solve a problem of statically what? Indeterminate. Okay, so like what I mentioned earlier, you can see for yourself that delta L and delta R are always what? Opposite in what? In direction. It can be due to mechanical loading. It can be later on we can be due to thermal loading, right? It is always in what? This is important, okay? It is always in opposite in what direction? Like what is stated down here. Okay, so you have to know that if both of them, when you calculate both of them have the same direction, the analysis is flawed. Means there's something wrong. Okay, so that is the rule that you have to know. And then from here, right, we can find RB. So from here we can find RB. Right, we can find RB by using delta L plus by delta R is equal to what? Is equal to 0. Okay. Right. So let's look at step number 1. Okay. Let's look at step number 1. Okay. So step number 1. Okay. Step number 1 is we're going to remove the support at point B. Okay. So I'm going to copy the diagram. Hold on. I'm going to copy this diagram. So the first thing we will do, right? So I can make the figure a bit bigger. So the first thing we will do is we are going to what? We are going to deliberately. So like you see what I've done is to remove the support at B and allow the structure to elastically deform. Okay. So the formula that we're going to use, you guys have seen this formula before, is delta or deflection is equal to PL over AE. And then the notation is when it's positive, it's in tension. Remember, right? And then negative is in what? Compression. So what we see over here is we're going to divide our structure into 4 portions, right? So we're going to call this, we're going to divide this into, this is my section 1, right? Because there's a load. Then this is my section 2. You have a change, is cross-sectional area. then we're going to divide again. Number 3, there's a load, right? And then finally, this is your last part.